Today we're going to take a look at thermochemistry, and although we'll see thermochemistry again later on in the year, we want to start off talking about it at the beginning of the year as well, because we know that all chemical reactions involve some sort of energy exchange. When bonds are broken, energy is required, and when bonds form, energy is released. And so we're going to take a look at some basic vocabulary around those changes and some review of energy. Okay, so to start off with, the definition of energy is the ability to do work or transfer heat. And since that's our definition for energy, we should probably know what work and heat are. So energy used to cause an object that has mass to move is called work, and energy used to cause the temperature of an object to rise is called heat. The SI unit for energy is joule, so we'll see the breakdown of where this comes from when we look at one of the energy equations in particular, but 1 joule equals, and notice it's a combination of the SI base units for mass and length squared divided by time squared. So it's 1 kilogram times meter squared divided by second squared is what a joule is defined as. You don't really need to know that, but we should recognize that joule is coming from the SI base units. Older units that we might see is the calorie, and 1 calorie equals 4.184 joules. A lot of times we'll work with kilocalories, which is that capital C calorie we see food reported as. A kilocalorie is, 1 kilocalorie equals 4.184 kilojoules, so that's another important relationship to make note of. Typically we'll be working with energy in joules in our reactions, or actually most likely in kilojoules, because most of our amounts of energy are substantially larger than the joule unit. Okay, so for types of energy, we've got kinetic energy. That is the energy an object possesses by virtue of its motion. And so there's the equation for it right here. So notice the little k just indicating that this is kinetic energy. And the equation is 1/2 times m times v squared. And mass is m and v is velocity. And the energy a substance possesses because of its temperature, we're going to refer to that as its thermal energy, and that's associated with the kinetic energy of its molecules. So that's going to be a very hugely important thing that we're going to talk about later on in the year, is that relationship between temperature and kinetic energy of molecules. Just as a practice calculation to see if we can apply what we know so far, we can pause the video and see if we can answer these questions. So what's the kinetic energy in joules of an argon atom moving at a speed of 650 meters per second? And then we should also try calculating a mole of argon atoms moving at a speed of 650 meters per second. And there is a kilogram mass conversion for AMU. And then again, remember, if we're going to come out with an energy unit such as joules, we need to make sure that our units that we're putting in are in kilograms and meters per second so that we get the right units. So pause the video, give that a try. Okay, so the answer to the first question, you should have come up with 1.4 times 10 to the negative 20th joules. And for the second one, you should have come up with 8,400 joules. Okay, so we've also got potential energy as a form of energy, and it's the energy an object possesses by virtue of its position or chemical composition. And where potential energy comes in to chemistry is, we can refer to it as chemical energy, and that's the energy due to the potential energy stored in the arrangements of a substance's atoms. So the most important type of potential energy for us, we're going to get into this later on in Unit 2 when we're talking about the electrons coming in and out of an atom and their energy levels. But here's the equation for electrostatic potential energy. And so we've got K here, which is a constant. We've got Q1 and Q2, which are electrical charges. So for example, an electron would have a negative 1.60 times 10 to the negative 19th coulombs. So capital C is a coulomb. And likewise, a proton would have a positive version of that charge. If I have a +1 charge, that's the value. If I have a +2 charge, it would be 2 times that, and so forth. D is the distance between the two charges, and the energy, this electrostatic potential energy, when it has an opposite, when the two charges have opposite signs, so the two charges that are interacting, two particles that are interacting, have opposite signs, then we end up with a negative potential energy, and that means attraction. And we'll notice when we study this later on that the lower the energy, the more stability there is. So again, we'll get into that a little bit more in Unit 2, but there's the version of potential energy that we're going to be talking about in chemistry. Okay, so some other important things when we're talking about the chemistry, energy of chemistry, is system and surroundings. And so the system is what we're going to call any of the molecules that we're interested in studying. So those would be the reactants and products, those things undergoing change in the process of the chemical reaction. The surroundings is going to be everything else. So notice in this picture here, we've got the molecules that we're studying, hydrogen and oxygen. And so those are the things that we're referring to as the system, and everything else is the surroundings. So the this piston, the cylinder, everything outside of the cylinder and piston, those are the surroundings. So it's very important when we're talking about the changes in energy, the changes in enthalpy, heat, and work, that we're looking at the perspective of what's the system, what's the surroundings, because especially when we're looking at calorimetry, we're going to be measuring actually the temperature changes in the surroundings, but really it's the energy that we're trying to find is for the system itself. So we'll have to watch sign conventions based on whether we're talking about the system or the surroundings. Okay, so let's take a closer look at work, because if you haven't had physics, or if you have, you might not quite understand how work's going to translate into what we do in chemistry. So although a lot of chemistry is work, but this is a different kind of work. So work technically is defined as force times distance, the distance over which the force is exerted, since we said we're moving an object over some distance. And really the only type of work we're going to be seeing in chemistry is the expansion or compression of gases. And so we'll call that pressure volume work. And when the pressure is constant, the sign and magnitude of the pressure volume work is this. So notice the negative in front of the P delta V being the change in system volume, P being the pressure. And if we take a look at a depiction of this, it'll make a little bit more sense why we have that sign convention. So notice this piston system here. So if I have the the pressure of the atmosphere pushing down on this cylinder, then it's at some pressure. We're assuming that when the gas expands, because the volume's expanding, the pressure can remain constant. So we know there's that relationship between pressure and volume. And so when my system is expanding, the system is pushing up on this piston, so it's pushing up on the surroundings. So my system pushes the surroundings, and that means it's doing work on the surroundings. So it's transferring its energy to the surroundings. So again, if I have a positive delta V, my system's expanding, then my system is losing energy because it's doing work on the surroundings. And so we can see that kind of depicted here with an actual reaction in a flask with the zinc and HCl and forming hydrogen. So that gas formation is expanding the piston. And again, if the volume of my system increases, that means it's doing work on the surroundings. So that's what makes W have a negative sign for a reaction that has a gas that's expanding, and a positive delta V. All right, let's take a closer look at heat, because we're not going to see, we're not going to be looking too much at work in detail. Most likely the work that my system does, it's going to be minimal in comparison to the heat exchange. So we're more going to focus on heat. That's something that we can more easily measure, especially with the equipment we have available. So energy can be transferred as heat. Heat always flows from warmer objects or higher temperatures to cooler objects or lower temperature. And that leads us to the first law of thermodynamics. So we've talked about what is energy, what's work, and what's heat. Those are our two forms of energy that we're looking at. We've talked about kinetic energy and potential energy. Now we've got the first law of thermodynamics, and that is energy is neither created nor destroyed. That should sound familiar because that's also referred to as the law of conservation of energy. It's one and the same thing. And notice that what we have depicted here is if my system has some amount of energy and it loses energy, the surroundings are going to have to gain energy by that same amount. So if energy is lost to the surroundings, then my system energy is going to be negative, but that means that the surroundings have a positive energy change. And if my system gains energy, so if it increases in energy, that same amount of energy is going to have been lost by the surroundings. So again, we're going to have a negative delta E if my system loses energy, and that energy has to be transferred completely to the surroundings if it loses it. And if my system gains energy, that means that the energy had to have come from the surroundings to have a positive delta E for my system. So making sure we're looking at this correct sign convention is very important. So let's take a closer look at internal energy. Internal energy, it is exactly what it sounds like. It's the energy of all the particles in the system that we're studying, and it's a sum of all the kinetic and potential energy of the components of the system. So we know that molecules are going to have, they have vibrations, they have rotations, we know that they're moving through space, they have a certain amount of kinetic energy, they have energy stored in their bonds. So anyway, we're talking about internal energy, all the different types of energy that particles can have. That's what we're talking about. This can also include energies of the nuclei, of the atoms, and the component electrons as well. Because we're talking about all these different types of energies, and we're talking about atoms and molecules that are so extremely teeny tiny, we generally don't know a value for internal energy. It's not something that we can calculate very easily. But what we can do is take a look at energy changes. And so by definition, the change in internal energy is going to be our final energy of the system minus the initial energy. So that's the setup for any delta anything, is final minus initial. So delta E, so the capital E being our internal energy, is final minus initial temperature. Or sorry, final minus initial energy. So if we have a positive delta E, that means that the final energy must be greater than the initial energy, and therefore the system absorbed energy from the surroundings. And likewise, the sign convention, if we have delta E less than 0, which means it's negative, that means the E final must have been less than E initial. So when I do this subtraction, it gives me a negative value, and that means the system released energy to the surroundings. Let's take a look then at how heat and work correspond with these signs that we just talked about for change in delta E. So when energy is exchanged between the system and the surroundings, it's exchanged as either heat or work. So you can see from these different depictions here with this vault, we've got, in some cases, if we've got Q, again, for the system, if Q is greater than 0, that means the system is gaining energy via heat. And if work is done on the system, then the system is gaining energy via work. So that's delta E greater than 0. If we're losing energy from the system via heat, then Q is less than 0. And likewise, if the system's doing work, then work is going to be less than 0. So these are kind of important to take a look at. Q is positive. That means the system gains heat. So again, Q being our symbol for heat. And if it's negative, it means the system loses heat. If W is positive, that means work is done on the system. So the system gains energy because of work being done to it. If it's negative, then work is being done by the system. So the system's transferring energy via work to the surroundings. And then for delta E, positive means net energy gain by the system. Negative means net energy lost by the system. Here's our equation for delta E then. So delta E equals Q plus W, and obviously then we need to keep track of what the signs are for what's being gained or lost. The vocabulary around heat energy being gained or lost, so notice in this system over here, whatever reaction is being done has resulted in the temperature going from room temperature to below room temperature, and so that is going to mean that it's endothermic. Now, we've talked about this in first year chem. The reason that a lower temperature for my system means it's endothermic is that energy has been transferred from the surroundings and stored in the chemicals in the system, and therefore we have a increase in energy, but again it's reflected in seeing a decrease in temperature of and technically it's the surroundings we're measuring the temperature drop of. So that's endothermic if my system absorbs heat energy, but again it's going to manifest itself as a decrease in temperature for the system, or sorry, for the surroundings, because the energy is being taken from the surroundings and put into the system. We have this as our example here. We see the light and fire and sparks coming out of here. So this is an exothermic reaction. So when heat's released by the system to the surroundings, well, that's why the surroundings are heating up and feeling the that transfer of energy, translating in terms of an increase in temperature for the surroundings. So endothermic, so thermic referring to the heat energy, endo meaning absorption or going into, and exo meaning exiting or leaving. And so what we're going to talk about later on in the year when we get to thermodynamics again is that many exothermic reactions tend to be spontaneous. The words for that is thermodynamically favored because they result in lower energy products, but we'll find that there are other factors that influence spontaneity besides just forming lower energy products. But generally we find the larger the negative delta H, the more likely the reaction will be spontaneous. And again, we'll get into that in the last part of the year. Okay, so let's take a look at this example. Take a minute, pause the video, answer the questions. So which process do we think is endothermic? Which process is delta E is less than 0? And which process, if any, is there a net gain in internal energy? And notice that the arrows are pointing different ways, meaning energy either going into or leaving the system, and then the size of the arrow is your order of magnitude. So take a minute and think about that. Pause the video. And our answers are, for A, the endothermic process is going to have to be 3, because that's the only one where we have heat energy being absorbed into the system. So the arrow shows it's going into the system, so that's 3. For B, which process, if any, has delta E less than 0? And that is actually none of them. So notice the total overall change, even though this system is losing Q, losing heat energy, work's being done on the system. So this is a negative sign for this. This is a positive sign for this. But overall, this is gaining energy. This is work being done by the surroundings on the system. And so this is a positive sign for that. And there's no Q to be talked about. So this comes out to be a positive delta E. And this one, again, heat's being added to the system, and this is a larger order of magnitude than the arrow of work being done by the system. So for B, it's none, and for C, then we have a net gain of internal energy, which would be a positive delta E for all of them, actually. All right, let's take a look at this question also. So we've got 2 gases, and we want to actually try what we saw depicted in the previous picture, but we just want to do it with actual numbers. So see if you can calculate the delta E. So pause the video and take a minute. And the number you should get is 239 joules if you calculate out the gains and losses. Now it's time to take a look at what we call state functions. And really what we've been talking about with delta E, we've talked about how to calculate involving, when our system undergoes heat change, whether it's gain or loss, and when work is done either by the system or on the system, we know that there's a change in delta E. And so delta E is actually what we call a state function. And really what a state function is it's something that the value of the energy of the system, even though we don't actually know exactly what it is at any given point in time, we know that it's a certain value depending on what state we're at or what condition we're on. So that means that a state function is something that it doesn't matter how you got to that state, all that matters is what state you're in. So if you look at the example that we have here, we have 50 grams of liquid water in the center here at 25 degrees Celsius. So that's our state that we're going to be focusing on. And whether or not my water started out as a liquid at the boiling point at 100 degrees Celsius, or if my water started out as a solid at 0 degrees Celsius, all that matters is when I am at 25 degrees Celsius with my 50 grams of water, there's a certain amount of energy that's there. And so it doesn't matter how I arrived at this particular amount of energy, all that matters is that this is the state that I have. So it's path independent, so it doesn't matter how you get there, all that matters is where you are. So from the school, as an example, I could go to the Burlington Mall by taking a right out of here and then taking a right onto Mall Road. and eventually I'll hit the mall. I could also go in through town and then go up and get on 125 and loop around and get off on the exit for Middlesex Turnpike, and eventually I would arrive at the mall. So again, the location of arriving at the mall, that would be an example of my state function. So my location that I end up at, that's independent of how I got there. Obviously, one way that I described takes a lot longer, takes a lot more gas, takes a lot more time, I'm covering a lot more mileage, but the pathway can be different, but the place I arrive, my location is the same. And so that's the idea of what a state function is. So when we're talking about the energy of a system, what that means for us is, the energy of the system at a certain given temperature. Even if I don't know that exact amount, I know that when I'm there, I've got a certain amount of energy. And again, it doesn't matter how I arrived at that state or at that amount of energy. All that matters is with that state comes a certain amount of energy, whatever that might be. Okay, so internal energy, as I already mentioned, it is a state function. It only depends on the present state of the system, not on the path. So delta E only depends on the initial energy and the final energy, and that's going to be something very useful to us in calculating delta E. Another thing we should talk about is, so the change in energy itself, or the internal energy, that's a state function. Heat, which is Q, and W, which is work, are not state functions. So you can see from this example here with the fan and the battery, if our battery is shorted out or discharged, the same amount of energy, the same total energy has been released. So we can see that here, but how we got to that energy release is what's different. So in one case, in this case, we're just losing all of the energy to the heat of the resistance coil. It doesn't matter, but that amount of energy went out as heat versus the battery being expelled by doing work and then also giving off some heat. So, and the energy, total energy lost is the same no matter what, and that's why delta E is the state function. But again, the heat and work are not state functions.